thank you very much for the introduction here, and also thank you to Jamir and the other organizers for this, I think, really interesting program here, and also for giving me the opportunity to speak. Yeah. So when I selected the topic, I somehow thought it must have to do something with dissipation, as the title indicates, and that's why I choose the topic which I present here, which is closest to what we do on dissipation. But now, looking at the other talks, I should have probably also more talked even about our other work on cavities, although this is not dissipative. But anyway, I stick with what I have, and I apologize if this is a bit too off topic. Yeah. So the talk which I present is motivated by experimental possibilities to control condensed matter systems out of equilibrium. And there are generally three ways which you can think of this. One would be real non-equilibrium steady states. You can think of current-driven metal insulator transitions. And the other big topic is Floquet engineering, which you probably very well know from quantum simulation. So periodic driving to engineer interactions. And that's also used in the solid and has been used in the solid, for instance, for band engineering, also for engineering magnetic exchange interactions, and even generating artificial magnetic fields. And the third theme in this context is the classic way, where you impulsively excite a system and then watch how it transiently passes through a sequence of possibly or hopefully interesting non-equilibrium states. Now, think about the topic of this conference. Which of these three would fit kind of best in the picture of dissipative systems? And obviously, the number three seems to be farthest away from it, in the sense that it's the relaxation of an isolated system. But this is precisely what I want to talk about in this talk. So let me try to explain what is the connection, or what I think is the connection. If you think of a relaxation of some quite generic many-body system, then this often happens on very different timescales, which, for instance, has been studied quite in detail in the context of quantum quenches, where you do a sudden change of some parameter at time 0, and then watch some observable as it returns to equilibrium. Yeah? So immediately after this quench, you typically have a short phase in which all degrees of freedom evolve quite chaotically, and there's little which can be said in general, but then the system relaxes into a so-called pre-thermal state, in which the system simply has gained some degree of universality, in the sense that its state is described, or well described, only in terms of few variables. Yeah, more than you need in thermal equilibrium, but still only few variables. And then finally, it goes back to equilibrium. Now, for example, what was a situation that has been studied a lot is when this quench is in the vicinity of an integrable point, where these slowly evolving variables are just the perturbatively corrected degrees of integrals of motion of this integrable point. Now, the idea is that if we look at this transient state here, it's really a state in which you have energy and particles still being exchanged between different subsystems. And by different subsystems, I mean different sets of degrees of freedom. So the question is whether this state can also be approached in a simpler way, I mean simpler rather than simulating the full time evolution, namely by describing it in terms of a true steady state of some suitably chosen dissipative system. And this is kind of the point to which I will also come towards the end of this talk. So this is the plan, what I will discuss in detail. In the first part, I will just, to set the stage here, illustrate two recent studies which show the emergence of such slow variables in the time evolution. And then in the last part, I discuss the steady state representation. Also, let me say that all the simulations or the numerical data which I present here are based on a method called non-equilibrium dynamical mean field theory, which is basically a numerical evaluation of Keldysh diagrammatics for strongly correlated systems. But of course, I will be happy to answer any questions on this, but I think this talk will not be the place to discuss the numerical details. So my first example, as I said, is here discussing the relaxation of an antiferromagnet after an interaction quench. So this was the PhD work of Antonio Picano, a student in my group in Erlangen, his first part of the PhD thesis, so I should really pay the credit, or part of the credit, to him here. So what we do is we consider the paradigmatic model, Hubbard model, on a bipartite lattice, yeah? So with interaction U and tunneling between the sides. So the bandwidth is just 4. I mean, this just sets the energy scale. And we are in a regime in which the interaction is now smaller than the bandwidth. And in this weak coupling regime, we know that the system would go from a paramagnetic to an antiferromagnetic with increasing U at a given temperature, as shown in this phase diagram down here. And now what we do is we will prepare the system here in this symmetry broken state, and then suddenly change the interaction to a lower value and see how the order parameter, for instance, relaxes. Yeah? And that's what is shown here. If you would make a very small jump here, and we see that the system, well, stays ordered, yeah, and even it would stay ordered after thermalization, simply because the energy density in the system, you know, would be like still below the energy density in equilibrium at an L temperature. So now we can make a bigger quench so that you would expect that eventually the energy density is large enough to thermalize it. But then you would expect, would see that in the short time dynamics, this pre-thermal state still remains ordered. And only when you make a really large quench here, there's another threshold upon which also the early pre-thermal state here goes to the disordered state. So this like transition between this pre-thermal ordered and disordered state is a dynamical transition which has been studied quite a lot. I mean, it's also quite related to similar physics in BCS superconductors. And there's like also interesting facts on it, such as non-thermal criticality. But it's not what I want to discuss here, because this is the relaxation into the pre-thermal state. And in this work, we would like to discuss now actually the evolution of this pre-thermal state. And for this, like Antonio has simply extended the simulation a bit. So from this short initial time, which I just showed you, just by like 2 orders of magnitude. Yeah. So I should say that this was really also a major technical or major aspect of this work, because as you know, with any quantum time evolution, and the same is true for this non-equilibrium DMFT, long times are kind of the key challenge. So here's some technical development behind in treating these integrals in the Keldysh formalism, but this is not what I want to discuss here, as I said. So now we can focus on these longer times, focus here, for instance, in a situation where the pre-thermal state is still ordered, and try to characterize it. Yeah? And to analyze this state, we can look at the spectral function and the distribution function. Yeah? So this is what I showed down here. And this is actually the local spectral function on one side of the lattice for the majority spin. So in experiment, it would be an ideal STM measurement measuring here the local density of states. And in the initial state here, you would find a well-defined spin density wave gap, which then in this pre-thermal state closes but doesn't disappear completely because the system is still ordered. Now, more interesting than that even is the distribution function or occupation function. Yeah, so you could always take the occupied density of states, split it into the spectral and occupation function, and then the occupation function here in equilibrium would be, of course, just a Fermi function. But now if you look in this non-equilibrium state, then it is not a Fermi function, but it turns out to be very close. It's a Fermi function just shifted here by some constant. And in the same sense, if you would do the same for the minority spin, you would find a shift in the opposite direction. Yeah. So this is really an example where you see that there's a universal form of the distribution function, not anything. So which is just characterized by one more parameter. So kind of a demonstration how the system here develops a state which is described by just one probably additional variable here. Okay, so the fact that this like non-thermal distribution would actually enhance or like maintain the symmetry broken state, although the corresponding thermal state is non-symmetry broken, is also something which in the end can be rationalized in this case quite well already in mean field theory. And I should only like briefly discuss it here. If you would discuss the spin density wave in mean field theory, then it would be determined by a gap equation, which is actually quite analogous to the superconductor. And so it has a density of states and this distribution function. And this gap equation can be solved not only with a thermal equilibrium, but with any non-thermal distribution functions. In particular, we can take the one which we have extracted from the numerics and check whether it would like support a non-thermal symmetry broken state. And that means we take one in which kind of the distribution function for like positive energies is shifted in a positive way, and for negative energies is shifted in a negative way. And indeed, if you solve the gap equation with this, you can construct like a phase diagram of the gap here as a function of the shift parameter and the effective temperature. And in this phase diagram, you see that if you go along a constant energy line in this non-thermal direction, you find that consistently this shift of chemical potentials here increases or supports the symmetry broken state. Okay, so this was a case where we have this emergence of these slow variables. Actually, this is not so much relevant for this talk, but this was another surprise of the study when we look at the time evolution of that. So usually we'd expect this pre-thermal state to basically go to the thermal state on a single exponential time scale, and this is what not happens here. So take one of these curves here. Initially, the order parameter decays, like this logarithmic decays exponentially, but then it really speeds up after some time. Yeah. So this is really clearly in contrast to this normal single exponential time scale here. Yeah. So actually, if you would have a single exponential time scale, this curve would look more or less the same. But if you would have a logarithmic time axis, but here you should stress here's a linear time axis, so it's really a speed up. Yeah. So I must say this is a numerical finding. We don't have a full conceptual understanding of this, but I find it still interesting because it shows that this slow degree of freedom, which has emerged here, has its relevance not only in the vicinity of thermal equilibrium, but rather in some pocket in phase space, which is further away from thermal equilibrium. Yeah? And this is kind of as if this was some kind of precursor of a metastability, where you would expect like long-lived states that are really detached from thermal equilibrium. Yeah? Okay. Okay, but as I said, this was an example for showing this emergence of slow variables. Now let me skip that. Let me come to another, my second example and make a jump here. This will be about photo doping in a Mott insulator. Let me just check the time quickly. Okay, yeah. So, yeah, anyway, I think you will get me a warning. Yeah. So this work here is done by a postdoc, Dasari, in my group, and also in collaboration with another postdoc, Chai-Chung Lee and Philipp Werner in Fribourg. Yeah. So the general model is the same. We have the Mott insulator, but now at large U. So, and there, you know, at half filling, you would have a transition here from a Fermi liquid at small u to a Mott insulator at larger u. And this Fermi liquid is like seen here by a narrow peak that corresponds to strongly renormalized quasi-particle band in the local, seen in the local spectrum. And then you can go to doping. There you would find this quasi-particle band at the edge of the lower unoccupied density of states here for the electron doped site, and on the edge of here this lower band for hole doped states. And if you heat up the system, you destroy the coherence of quasi-particles that's known, and you go to a so-called bad metallic phase. And now what we can imagine is that we start from here, we do some photo excitation, and then the system is coupled to a dissipative environment, like phonones or whatever, and it returns. And we are interested in this process, this return process, so we would simply prepare a system initially at high temperature and then see how it relaxes back. No? Also in this case, this dynamics at shorter times has been investigated a lot, and so here we, in this publication here, we have extended the time scale, and so just for the sake of like simplicity, all the results I presented are from here, although some of the ideas are also in some of the earlier publications. But anyway, as I said, we prepare the system at high temperature here, temperature of the order of the bandwidth, and then see how it relaxes in the presence of a bath, which is a much lower temperature. And this is the kinetic energy, which you can see here. It has clearly two time scales, a fast evolution and a slow, while the other quantity that's of interest here, the number of W occupied sites in this Mott insulator, would just show a single time scale. Yeah? Okay, so in this regime here, the state now has kind of an increased number of W occupied sites and holes as compared to an equilibrium state at the same energy. So you can more or less understand it as a kind of a system, Mott insulator, which is simultaneously doped by hole-like and electron-like carriers in this regime. This can actually also be understood in the language of a TJ type model, but I don't want to discuss it here now. And now we can again look at the spectral function. Yeah, in the initial bad metallic phase, there's no signatures of quasi-particles, just 2 peaks. And then, so if the system would finally relax, it would have just this electron-doped quasi-particles, just because this particular simulation was starting from an electron-doped state. But the interesting thing is in the intermediate state now, it has like 2 quasi-particle peaks, one at the one hole-like and one electron-like quasi-particle peak. Yeah, so in this intermediate state, one really has kind of an unusual now 2-species liquid, if you like. Yeah. And by looking at the self-energy, we also find that this is not a true Fermi liquid, but rather something that is called, reminiscent of a resilient quasi-particle strange metal, but this is also what I would like to skip here. Yeah? And now again, we can look at the distribution function, which is plotted here. Yeah? So this plot actually doesn't show the directly distribution function, but the logarithm of ratio of occupied and unoccupied density of states, so that a straight line would correspond to a Fermi function with a shifted chemical potential. And this is indeed here found in this relevant spectral regime. Yeah. So again, we have the establishment of a like state which has this extra kind of chemical potential and extra like variable. Also at this point, I can stress the universality of this state. We can do a completely different protocol, for example, simulate a photo excitation instead of this starting from a high temperature state. And if we adjust the variables, would have precisely the same spectral function in this state. Okay, so to sum up, I've shown you some examples in this relaxation. Brings the system in a transient non-equilibrium state, which still has quite universal distribution function. So now I come to, in the last minutes, to the second part where I try to describe this non-thermal state in terms of a dissipative auxiliary state. Yeah. So the idea is quite simple, and it's basically what you know from your elementary thermodynamics. If you have a system which is an exact conserved particle number, then that means that if you couple a particle reservoir to it, then the number just adjusts to the chemical potential of the reservoir, no matter how weak the coupling is. At least that's the usual story. So there are 2 facts now. One is, the response in this case to an external reservoir is completely non-analytic, in the sense that, as I said, an infinitesimal coupling gives a finite path, a finite response. And the second, the state which you have is universal. It doesn't depend on the spectral density of the bath, but just basically on the number of particles in there. Now, this concept can be generalized to the case where you have almost conserved quantities, where just the coupling to the bath more or less has to have a finite value in order to activate these slow degrees of freedom. This was developed in a nice work by Sala Lenarczyk, Achim Roche, and others here. And what we propose here is to use this in order to also explore transient phases of photoexcited solids. So for this Mott insulator, where our variables are doubly occupied sites and holes, you could just imagine to put both a filled bath and an empty bath, where the filled bath is at high energies, the empty is at low energies, and this kind of tries to pump a population inversion in the system, and eventually leads to this extra occupation in the upper band. So how many minutes do I have?
3 minutes.
Okay, yeah, this should be okay. Okay, so and now we can analyze this. So we take our spectral density of the Hubbard model here. This is actually now, apologize for this, the spectral density in the antiferromagnetic phase, simply because there is more interesting spectral structure here. This is the upper band, the lower band, and in the presence of antiferromagnetism, the single particle spectrum shows the substructure, which is spin polaron bands, basically the electrons interacting with the spin background. And this can then be also used to analyze what's going on here. Yeah? And now we put our bath here, basically coupling a particle reservoir to each site. And the structure of this bath really is completely irrelevant, as it should be. So here we put a filled bath here and an empty bath here, and then the system in a steady state gives a distribution function here and here. Yeah. So this is electron filling more or less in the upper band. Yeah. And the key thing is the shape of this distribution here is really independent more or less of the bath. So here I have a bath which is a sharp edge shape, but if you look at the distribution functions here on a log scale for different bath couplings, they do not feature any of these edges here. And you can also put any other type of bath here, any other like spectral densities, and look at the occupied density of states. They basically are almost the same here. Yeah, so this is really this idea of that you can, in this case of that this W occupancy is actually a slowly evolving variable, just prepare it in a dissipative way. Yeah? And so now we can, for instance, here look at one of these cases and also look again at the spectral function. So this was this upper band with this spin polarone structure. And you will see that as you increase the doping here, then really these spin polarone bands get decreased. That's what we have. And now the interesting and key thing is that you can again compare this really to a photodoped state obtained from a real-time evolution. So really simulating the laser excitation, letting the system evolve. And this is this dashed line here. And the key thing is that really if you fix in the both states just two variables, that means the two have the same order parameter and say the same upper band occupation, and really the spectral shape of this spin polaron bands is the same. Okay, so with this, my time is almost up. If I want to leave something for discussion, I think we use this to explore the phase diagram in a more non-trivial sense, the phase diagram of a superconducting phase in this photodoped state, but we can also leave this for questions. And with this, I would like to go to the conclusion here, or probably I would have the time. Anyway, so the conclusion is I have shown you two examples where you really see explicitly in the time evolution of some correlated systems how this like quasi more universal state evolves, which in these cases is described by two chemical potentials. And in the evolution, there was kind of a mystery here, I would say, for the antiferromagnetic case, which is to be understood. And I've shown you the idea of exploring such photo-excited phase diagrams using a dissipative analog. And of course, the most important thing is to thank the people who have been involved, like Antonio Picano, PhD student I've mentioned already, and Dasari, who were responsible for the first work, and Chai-Chung Lee is really the postdoc here behind this dissipative preparation of the study of these states. And with this, I thank you for your attention.